In this video, we'll be learning about binary search. But before understanding what binary search is, let's understand what searching is. So, searching is looking up in a list. So, if we are given a list of elements and we want to see if we have the element 23 present in the list or not, so that looking up in the list to find whether 23 is there or not, or to return the index of 23, that is called as searching. And in order to search the element inside the array, there is one very basic way, one brute force way, which is we go into the array, check first element, see whether it's equal to the target or not, then check the second element, then third, then fourth, till we find the actual target value. This is called as linear search. This is called as linear search, where we are checking each and every element one by one, starting from one end of the array till the end. So this is linearly we are parsing the array and searching for the element that we are looking for. Contrary to this type of searching, we have another type of searching which is called as binary search. So if we look at the name, it is binary. So something to deal with by, which is equal to 2. So before applying and understanding binary search, there are 2 points to remember for binary search. Binary search can only be applied on sorted array. So we cannot use binary search on any random array where the elements are randomly placed. If you want to apply binary search, we'll either have to sort the array or we cannot apply. We'll have to solve the question by linear search. So we need to have a sorted array in order to apply binary search. And the second point is that binary search also uses the concept of divide and conquer, just like we saw for merge sort. So binary search is based on divide and conquer, where we divide the entire array into smaller parts and then try to find it. And when we say divide, so as we see, it is binary. So every time we divide the array into two halves, and then we see where we need to go. Now let's see how binary search actually works. We have this array, and as you can see, this array is sorted. Again, we divide the array, divide it into two parts. Now since two parts are involved, there is a middle element that we need to find, middle index element. And now in order to find a middle index element, there would be two things that we would be needing: the start of the array, which would be represented by low, and the end of the array, which would be represented by high. Again, we use this formula, low plus high minus low upon 2. So this is how we calculate the middle element. This formula, we studied about this formula in the merge sort video as well, and I have described very well why we use this formula. There is another formula that we also have, but we prefer this formula. If you want to know more details about it, you can just go watch the merge sort video. So this is the formula that we use for calculating the middle element. Now let's actually implement binary search and see how we search for our element. So we have the low value. This is the actual array that we have. This is the array. This is the division. We start from 0. 0 is at low 0 and last element is at high 7. Now we calculate the middle point. Middle point would be at index 3, which is 5. So we go ahead and check, is 23 greater than 5? Yes. Since 23 is greater than 5 and we know that this array is sorted array, so we also would know that all the elements to the right side of the current element, which is 5, would be greater than 5, which means if we want to search for 23, it will either be present here or it will not be present in the element. So we only need to search on the right side. There is no benefit of going ahead and searching at the left side. So that is why every time we find the element, we check our target element with that middle element and see whether it is larger than the middle element, smaller than the middle element, or equal to the middle element. So if it is equal to, then that is what we have reached the answer. We don't need to do anything further. We'll just return the index of that element, or true or false, based on whatever we are solving, and we'll get the answer. But if The middle element is larger than the element, so we know our target element would be present the left side, and so on. So here in this case 23 is greater than 5, so we move to the right hand side. How do we move to the right hand side is, for now we'll change the low. The low would be changed to middle plus 1. So our middle was 3. Now since we know we have to move to the right side of the array, so we change the low as 4. High would remain same because we have to traverse to the right side of the array. Now again we calculate the middle element. Middle element would be somewhere around 5. Now we check it with the fifth element, which is 19. So 19 is again smaller than 23, so again we move to the right side. So now we have only 23 and 52. Again we calculate the middle element. 6 plus 7 equals to 6, so now we point at 23. Now 23 is equal to 23, that is why we have found the element and we return the solution. But there could have been a case, in case instead of searching for 23 we are searching for an element which is not present in the array. So we replace this by 24 for example, so it would be 20. So if we have this same array and instead of 23 we were searching for 24, so all of the condition would remain same, just the last one. When we are at the sixth index we hit the element 23, we'll see 24 is greater than 23, so we do not return the answer, we move to the right side because we'll have to see for the right hand side. Now mid was 6, low was 6, high was 7. Now we move to the right side, so our low becomes mid plus 1 equal to 7, and high also become is already 7. Now we know, so when our low is 7, high is 7, so our mid is also going to be 7 plus 7 minus 7 upon 2, which would be 7. So we go ahead and compare it with the last element. If it's not found, we again move to the left one. Now our low remains 7, but our high would become mid minus 1, which is 6. Now the condition fails. Low always has to be less than high. Since here low is not lesser than high, we return, and this is what becomes our base condition. So whenever we are performing recursion or any iteration where we have to end somewhere, we have a while loop. So here we'll either run a recursion or we use a while loop. So wherever we are in a loop, there is some base condition which would be returning the loop, which would be ending the loop. So this is the base condition for this, where we have to see our low variable. If it is lesser than the high, then only it executes to the next loop, else it returns. And that is how we use binary search in order to find an element. Now let's look at the time complexity. So we see in the first place, if we have n elements in this first recursive call, we divide the n elements into half. So we divide it into two parts and we do not use the half part, we only use one half. So in first case we parsed n elements, in the second case we'll be parsing n by 2, n by 4, and so on. So if we assume we take around k steps to reach the last stage, the last recursive call, the last recursive call would end when we have only one element in the array. This is the worst case. The maximum, mostly if we find the element, we may find it in between, but we'll assume the worst case. So in the worst case we'll reach the end of the loop where there is only one element left at the end. So in this case, again if we look at this is of the form n upon 2 raised to power 0, n upon 2 raised to power 1, 2 raised to power 2, and so on. So the kth step would be n upon 2 raised to power k, and this would be equal to 1. Why 1? Because the base condition is that before the base condition we end the loop when there is only single element left. So n upon 2 by k would be equal to 1. If we take log, it would be log n equals to k log 2, and that is how we get the value of k equals to be log n. So the time complexity of binary search is log n, which is smaller than the time complexity of linear search, and the time complexity of linear search is O of n. And why O of n? Because in linear search we are actually parsing each and every element in order to compare it with our target element, and that is why its time complexity is more. And binary search is the more efficient way of searching any element in an array, but the precondition being that it has to be a sorted array. Now let's have a look at the space complexity. In space complexity, the extra variables that we take in order to apply binary searches, the low variable, the high variable, and the mid, which is constant. Like we won't be actually using any more elements than these three variables. So because of this, our space complexity becomes O of 1. So now let's move to the code of binaries. We'll start with a method. We need one variable which will start from the first, which will point to the first index of the array, and then our high would be equal to the length of the array minus 1, because that is how we'll be using high. So the condition would be while low is less than equal to high, till then we'll be looping through the entire array. Now we'll be calculating the midpoint, so we use low plus high minus low upon 2 as the formula for calculating the midpoint. Now we'll go ahead and check if our target equals to the element that is present at our mid. If it is present, then we simply return the index mid, because okay, we have to, let's return int, and if we'll see if target is greater than the element present at mid. If it is greater than the element present at mid, then we know what we need to do. That means our element will be present in the second half of the array, So we'll update the low of the array to mid plus 1. So we'll be just leaving the first part of the array, and then we move to the second part. And if that is also not the case, that means the target, if it's not equal, it's not greater, that means it's smaller. If it's smaller, so we'll be updating the high value equals to mid minus 1, and that is what we'll do. If we do not find the element, that means we won't be returning here, and we'll be reaching the end of the array. In that case only we return as minus 1. So let's see how we get the answer. So this was the array, and we were searching for 23, and 23 is found at index 4. So this is working. That's all for today's video. Thank you.